Hi everyone, welcome to lecture 17. Today we will talk about some advanced topics related to state estimation. As you recall, weighted least square method is one of the most common techniques that are used for solving the state estimation problem. However, this technique is not ideal and has shortcomings of its own. So we're going to talk about some of these shortcomings and discuss some alternative approaches to weighted least square method. In addition, state estimation is subject to some biases that come from non-idealities in measurements, in the system model, in assumptions that we make. We're going to go over some of these non-idealities and biases, and we'll talk about some mitigation techniques. Before we get started, let's review what we learned about state estimation. In the power system, we have a series of states. These are the voltage magnitudes and phase angles at different buses. We also have a series of measurements. We show the state by X and the measurements by Z. Every individual measurement Zi is going to be related to the states through a nonlinear function that I show here as h of I. Ideally, you would expect Zi to be equal to hi of X. In practice, however, this is not the case because of measurement inaccuracies, errors, modeling inaccuracies, and all sorts of non-idealities. So the difference between each measurement Zi and the corresponding function hi of X is called a residual. The objective behind weighted least square technique is to minimize these residuals. So we form an objective function j of x, which is the summation of all these residuals squared. However, we also acknowledge the fact that different meters have different accuracy levels. Some meters are more accurate, some are less accurate. Obviously, we would like to give a higher weight to meters that are more accurate. We model these by associating a measurement error to individual meters. This would be your sigma I, which is essentially the standard deviation of that particular meter. This way, the problem becomes a weighted least square method. So now j of x is going to be sum of residuals squared divided by sigma I squared, which is the variance of those meters. We can write this in matrix form, which is going to be z minus h of x transpose times w times z minus h of x. W is a diagonal matrix whose diagonal entries are essentially 1 over sigma I squared. Now to find the states of the system, we have to solve this optimization problem. And in order to do so, we have to find the derivative of j with respect to x and set it to 0. You recall from our lecture last time that if you do this, you're going to find an equation of the form x at step v plus 1 equals x at the previous step plus h transpose wh, the entire thing inversed, times h transpose w z minus h of x, as shown in this slide. This is an iterative approach. Often we start from a flat start where all voltages are 1 per unit and all phase angles are 0 degrees. And we continue this iteration until we reach convergence. Sometimes this is shown by a deviation in x's. In other words, x of v is taken to the left-hand side and the equation becomes delta x at v plus 1 equals sum matrix times h transpose times w times z minus h of x. Now, one of the most important parts of state estimation through weighted least square technique is this particular matrix G that I'm showing on this slide as h transpose wh. We call this the gain matrix. And some of the shortcomings of the weighted least square technique are actually associated with this matrix G and the way we want to invert it in every iteration. Now, what do we know about matrix G? First and foremost, it's symmetric. It is also sparse, although it's not as sparse as matrix H. This is because G is derived by multiplying H transpose by W by H. So in this process, some of the sparsity is going to go away. Generally speaking, it's a non-negative definite matrix, meaning that all the eigenvalues are non-negative. They're either 0 or positive. If the network is fully observable, it actually becomes positive definite, meaning that there won't be any zero eigenvalues. All eigenvalues are going to be positive. Now, G is relatively sparse, but once you invert it, it's going to be a full matrix. And as you saw in the previous slide, you have to invert G at every iteration. This could be problematic because it takes a lot of computational resources. So to solve this problem, we sometimes use a decomposition known as Cholesky decomposition. Through Cholesky decomposition, we write G as a multiplication of two matrices, a lower triangular matrix L and its transpose. Then, by taking G to the left-hand side, we avoid taking the inverse. So the equation now becomes G times delta X at step V plus 1, which notice here I replace G with L times L transpose, equals H transpose times W times Z minus H of X. Now for the left-hand side, we first use forward substitution, then backward substitution to solve the problem. This avoids the need for inverting G at every iteration, and it saves a lot of time for us. Cholesky decomposition helps us a lot. It saves a lot of time and a lot of computational resources. However, if the dimensions of the system are large, then even Cholesky decomposition is going to be very resource intensive. Finding that matrix L and doing the backward and forward substitution could take a lot of time and a lot of computational power. So we come up with another alternative approach, which is called decoupled weighted least square technique. Here we take advantage of two important observations. Number one, if you start with a reasonable initial condition for the states of the system, the elements of matrix G do not change a lot. So we can sort of assume that G is kind of a constant matrix. Now, what is a reasonable initial condition? In power systems, fortunately, we know that this would be the flat start. All voltage magnitudes 1 per unit, all phase angles 0 degrees. The second important observation is the inherent decoupling behavior that we know in power systems. P, active power, is more than anything related to delta, and Q, reactive power, is more than anything related to V. So the relationship between P and V and Q and delta is relatively weak. This is in particular true for high voltage transmission systems. In a situation like that, we can decouple the weighted least square technique into two parts, one part for P, one part for Q. Notice here my measurement matrix is going to be decomposed into two parts. One would be anything that is related to active power, could be active power measurements themselves, could be phase angle measurements, and anything related. The other part is going to be any measurement related to reactive power. Again, could be the reactive power measurement itself or the voltage magnitude or things that are related. Every other matrix also is going to be decomposed into portions that are relating active power, reactive power to voltages and phase angles. Now, assuming that the decoupling is there, I can actually break my equations into two similar equations in structure. One would be the equation for delta, one would be for V. So instead of solving one equation for X and iteratively updating the X value, I have two independent loops, one for delta, one for V. Obviously, the dimensions of the problem are going to be much smaller, and as a result of it, the convergence is going to be a lot faster. A very simple alternative approach to weighted least square technique is DC state estimation. Similar to DC power flow, here we make a lot of simplifying assumptions. We assume all voltages have a magnitude of 1 per unit. We ignore the resistance of the lines, and we ignore the shunt susceptance of the lines. So the power transfer from node I to node J would simply become delta I minus delta J over X of Ij. Where is this equation coming from? Remember that if I don't make any of these simplifying assumptions, my Pij would be Vi times Vj divided by Xij times sine of delta I minus delta J. I replace Vi and Vj with 1 and replace sign of delta I minus delta j with delta I minus delta j itself. So I remove nonlinearity altogether. The measurement equations this way becomes linear, very simple, and typically you would only be interested in either phase angle measurements or active power measurements. So your ZP, active power measurements, would be some matrix HPP times the vector of delta plus the error vector. And the good news again, HPP here is going to be a constant matrix, which is only a function of reactance values of the series branches. Now DC state estimation is going to give us a very approximate solution. This is typically used when we don't look for a lot of accuracy in the states of the system. Instead, we want to get the values, approximate values, relatively quickly. So in a situation like that, simplifying assumptions are justified. The computational burden associated with inverting matrix G or using the Cholesky decomposition is one part of the problem. In certain situations, it is possible for the weighted least square technique to become numerically unstable. This is a situation in which matrix G becomes ill-conditioned or singular. There are some scenarios in which something like this might happen. Some examples could be using measurements that have very high accuracy rates. For example, consider adding pseudo measurements such as KCL or KVL. We know that these measurements are very, very accurate. So they're going to have very large weights associated with them. This could make the problem unstable. Or interestingly enough, if in one system you have short lines and long lines that are connected to the same bus, this could, under certain situations, make the problem unstable. We're going to see a couple of examples shortly that will show you why something like this might happen. Now, there are solutions to this. We're not going to get into the details of these solutions, but I just wanted you to be aware that in certain cases, people have proposed solution techniques in which you avoid using G altogether. So if you sense that it has a chance of becoming ill-conditioned, you deal with matrix G directly and you factorize it without considering G. Another approach that has been used in the literature is to look into measurements, virtual measurements, pseudo measurements that have very high weights, and instead of incorporating them into the objective function, include them as equality constraints. So you solve your optimization problem subject to these particular constraints being met. We're not going to get into details because this is kind of outside the scope of our talk today, but if you are interested in the first reference in this presentation, there is some additional information, some additional techniques that you can refer to that for getting more information. Let's do the first activity. Consider the 3-bus system shown in this diagram. And in this analysis, we're going to do DC state estimation. What I'd like you to do is to find the gain matrix G for this system. Consider I have two measurements. One is the power flow from bus 0 to bus 1, and the other one is a pseudo measurement that is essentially the null power injection. What does that mean? This measurement says P1 equals 0. In other words, the entire power that is transferred from bus 0 to bus 1 is transferred from bus 1 to bus 2. In this analysis, assume that both lines have reactance values of 1. At this point, I'd like to ask you to pause the video, work through this exercise, and when you feel like you're ready, hit play to see the solution. First, let's define the states and measurements. The states of the system are delta 1 and delta 2. Notice this is DC state estimation, so voltage magnitudes are 1 per unit. Also, I can take bus 0 to be my reference bus, whose angle is going to be 0. Measurements, on the other hand, would be P01 and P1. Based on the equations for DC state estimation, P01 would be delta 0 minus delta 1 divided by x01. Plug in the numerical values and you will get minus delta 1. P1, on the other hand, would be derived by writing the KCL at bus 1. So P1 essentially is going to be P12 plus P10. If you write the equations and plug in the values, you will get 2 times delta 1 minus delta 2. Now I'm ready to write my measurements as a function of my states. So my measurement vector z would be a matrix minus 1, 0, 2, minus 1 times my states. If we form the gain matrix G, and if you recall, it being H transpose times W times H, this is what I get. W1 plus 4 times W2 minus 2W2 minus 2W2 and W2. Notice the null power injection measurement for P1 is a highly accurate measurement. So W2 associated with that is going to have a high value. However, P01 is not going to be a highly accurate measurement. So the weight W1 associated with that is likely to be relatively small. If you find the determinant of matrix G, it becomes W1 times W2, likely to be a small value. If the determinant is small and close to 0, the matrix has a high chance of becoming ill-conditioned. And this, again, could be one of the reasons for this problem to become numerically unstable. Let's move on to activity 2. Here we consider the same system, and again we're interested in DC state estimation and we would like to find the gain matrix G. However, in this case we have two measurements, P01 and P12. Both have weights of 1, meaning that none of them is more accurate than the other. In addition, we assume that the ratio between x12 and x01 is k. This could be thought of as the ratio between the length of the line connecting buses 1 and 2 and the length of the line connecting buses 0 and 1. Again, I'd like to ask that you pause the video at this point, do the calculations. When you're ready, hit play and you will see the answer. If I follow the same approach as I did before, P01 will become minus delta 1 over x, and P12 becomes delta 1 minus delta 2 divided by k times x. Notice I replaced x01 with a constant x and x12 as k times x. Now if I write the measurements as a function of states, I will get a matrix as I have shown in this slide. 1 over x times minus 1, 0, 1 over k, minus 1 over k. Now, let's form the gain matrix G. G is going to be H transpose times H. Notice I skipped W because both meters have an accuracy of 1, so W essentially is going to be an identity matrix. If I find G, I will get a matrix whose entries are going to be k squared plus 1, minus 1, minus 1, minus 1. If you find the determinant of this matrix, is going to be equal to k to the power of 2. Now, if I have two lines connected to bus 1, one of them very short, one of them very long, k becomes very small. K squared is going to be even smaller. If it becomes very, very small, it adds to the chances of instability of the problem. So this is another example that shows you a seemingly decent problem could lead to instability when you use weighted least square technique. In addition to the computational efficiency of the weighted least square technique, we are interested in knowing how accurate the results are going to be. Now, statistically speaking, a state estimation approach based on weighted least square technique is an unbiased estimator if and only if two conditions are met. Number 1, the model has to be accurate. Number 2, the measurement error has to be statistically distributed. And if you recall from our previous lecture, this means that all measurements have to have an average value of 0, meaning that they do not systematically overestimate or underestimate, and also measurements are going to be statistically uncorrelated with one another. Are these assumptions correct? Sometimes they are, sometimes they are not. In practice, there are certain situations that we may actually have been simplifying the problem too much. For example, a lot of times we assume that there are no harmonics present in the system. We only consider a single frequency of 60 Hz. Is this true? Maybe yes, maybe no. We also assume that the system is symmetric, some assumption that is typically valid for transmission systems, but often not for a distribution system. We assume the system is balanced. Again, in distribution systems, this is not the case. In addition, we sometimes assume that the dynamics of the system do not change so much between non-simultaneous measurements. So I can take one state estimation now, 5 minutes later, 2 minutes later, 10 minutes later, I can take another one, and during this time, not much change occurs in the system. This again may or may not be true depending on the system that you're dealing with. So what are the sources of non-ideality? First, you can have biases due to unbalanced operation. If you have unbalanced operation, you're going to have some errors in your measurements. You're assuming a balanced operation, so you're making assumptions about the three-phase values, which are not going to be true anymore. So this error in measurement that I'm showing here as delta z is going to be incorporated into your equation. If your actual z equals z of t, what you assume it is, plus delta z, error due to imbalance, and if you plug in this value in the equation for iterative approach of x, your x will become x of t, what you get assuming that the system is balanced, plus some error value, which would be H transpose WH inverse times H transpose times W times delta Z. This would be your bias. This would be your error. This would be the inaccuracy that you have in the state values that you have obtained, assuming the system is balanced. The other source of non-ideality would be the bias due to system asymmetry. You could assume that the system is symmetric and say my measurements z are a function h of s of x, s for symmetry. In practice, however, if the system is not symmetric, then you're going to have errors in the values of the series and shunt branch impedances. This, you can show it here as a matrix or a vector delta h of x. And if you incorporate this into the calculations, you will find an error which is associated with the actual values of x. Third source of biases, as I mentioned earlier, would be harmonics, which could affect the values of the voltages at different nodes. We also could have measurement errors. For example, as we talked about it last time, we assumed that no meter would be systematically underestimating or overestimating the measurements. This is only true if all the sensors, cables, converters, and everything are properly calibrated. If this is not the case, you could have some systematic errors in measurements. In addition, some individual measurements could have some residuals which are very, very high. This again could cause problems in state estimation, and we'll discuss it shortly. Lastly, we could have biases due to measurement time skews. What is the time skew? In state estimation, we didn't really talk about the timestamp of measurements. We assume that the measurements are available, we plug them into the equation, and we find x. Is that the case? Not really, because typically these measurements are coming through the SCADA system. The SCADA system has a process in which it starts polling different RTUs one after the other. It's going to take some time when it goes from RTU1 to RTU2 to RTU3 and so on. If the system is small, this could be negligible. However, if the system is large or it has some fast dynamics, it is possible that, let's say, you have 1,000 measurements. By the time you get from measurement 1 to measurement 500, the dynamics of the system have completely changed. So you will find state estimation for some snapshot in time which doesn't really exist, and this would be inaccurate for your system. In the next few slides, we'll talk about some mitigation techniques that could alleviate some of the biases that we saw earlier. First, let's focus on unbalanced operation and asymmetric network. If you have a system which is unbalanced or does not have full symmetry, which is typically the case for distribution systems, you're not going to be able to do a single phase positive sequence state estimation anymore. You're going to have to do what we refer to as three-phase or multi-phase state estimation. Here, for each bus, you consider 6 state variables: V1, V2, V3, delta 1, delta 2, delta 3. Measurements are going to be three-phase as well. So you're going to have individual voltage measurements, individual current measurements, individual active or reactive power measurements. As you can imagine, the dimensions of the system would increase dramatically, and so does the convergence time. So it could take a long time for the problem to converge. Sometimes, especially if the problem is ill-conditioned, it's not going to converge at all. Next, let's consider a system that has harmonics. The solution to this should be obvious. We have to do a state estimation in which we consider harmonics. This is called harmonic state estimation. As you can imagine, this can dramatically increase the size of the problem. If you consider H harmonics for an n-bus system, and if, let's say, on top of it you want to do three-phase state estimation, the number of state variables would be n times H times 2 times 3. Just plug in some numbers and see how big of a problem you're going to get. In harmonic state estimation, we often try to use measurements as voltages and currents instead of active power and reactive power. There are different reasons for it. First of all, we're more comfortable with the notion of voltage harmonics and current harmonics. For active power and reactive power, this is not the same. In addition, defining the error values and standard deviation values for P and Q meters in the presence of harmonics is not really easy. And lastly, in power systems, we don't really have a universally accepted definition for reactive power in the presence of harmonics. Different groups, different researchers have different conventions for it. So because of this, we try to use V and I measurements instead. Another variant to state estimation is what we call a robust state estimation. Why do we need this? Consider the weighted least square technique. If one of the weighted residuals is too large, it can influence and affect the outcome of the state estimation. It can make every individual state biased and inaccurate. Now, before we talk about solutions to this problem, let's discuss an important feature of a state estimator: breakdown point. What is a breakdown point? Imagine you have a set of M measurements. Let's call it Z. This is going to give you an estimate for the states of the system. Let's call it X. Now imagine some of these measurements become corrupt. Let's say M prime data points become corrupt. So with the new set of measurements that I call here Z prime, I'm going to get a new estimate X prime. Clearly, this is not going to be accurate and will be biased. I am now interested in quantifying the bias. So I look at the individual states, individual voltage magnitudes, individual phase angles. I compare the value that I obtained with the corrupt data points with the value that I obtained with correct data points. So I compare xi's with xi primes. And I pick the biggest deviation. I consider that to be the maximum norm of the bias. Now what I do is I start increasing the number of corrupt data points. I first start with one data point that is corrupt. I look at my bias. 2 data points, 3 data points. I continue monitoring the bias until the point that it becomes unbounded. It becomes infinity. That is the breakdown point. Numerically speaking, we consider the number of corrupt measurements that give me an unbounded bias divided by the total number of measurements as the breakdown point for that particular estimator. This is an analysis that we can do for any type of estimator, not just the ones used in power systems. And they show you how inherently robust a state estimation technique is. Fortunately, there are solutions to deal with weighted residuals that are too large. The first and perhaps the easiest approach is to basically identify the outlier values. If you look at a measurement residual that is too big in a sense that it doesn't make sense, look at it. If it doesn't make sense, remove it. If you look at a meter accuracy that is too high in a way that it doesn't make sense, again, do a sanity check and remove it. This way you get rid of all these weighted residuals that are too big, and hence you remove that source of bias. Sometimes, however, this is not possible. Sometimes it's not possible but to remove these outliers and detect these outliers by just looking at the residual values. In situations like that, we use what is called a non-quadratic estimator. Here, you minimize an objective function, I show here as j as a summation of I from 1 to m, of a function f times ri. Ri tilde is essentially the weighted residual, is Ri divided by sigma I. Notice in weighted least square, f of Ri tilde is essentially Ri tilde squared. So you look at Ri squared divided by sigma I squared. However, when you square the residual or the weighted residual, what happens is if its value is too big, by squaring it, you're making it even bigger. So here, we try to avoid this problem. We use the square value for weighted residuals that are not too big. But if they become too big, then we're going to be bounding it. In this diagram, I'm showing 3 examples of the function f that you can use. The red line is essentially a linear function. So instead of squaring the weighted residuals, you just look at the linear values. The black line considers squaring the values until some threshold, a user-defined threshold, beyond which you're going to be linearly increasing it, not squaring it anymore. The blue line, on the other hand, tries to square the values until some threshold. Beyond that threshold is not going to be increasing them anymore. It's going to cap them at some value. So here, if you have weighted residuals that are too big, you're essentially reducing their impact on the solution of the state estimation. This, of course, could have the disadvantage of making your optimization problem less tractable, or I should say less easily tractable, because as you know, quadratic form is going to be the easiest way to solve this optimization problem. The moment you move towards non-quadratic, you're likely to run into some numerical problems. However, if you have weighted residuals that are too big, this is one of the effective ways that you can deal with them. Let's assess the notion of breakdown point through a simple exercise. Imagine you've given 5 measurement points, 0.9, 0.95, 105, 107, 109. And you have different estimators. One is basically looking for the mean or average value of these measurements, and the other one is looking at the median of these measurements. We're interested in knowing what the breakdown point is for each of these estimators. In order to do that, what you're going to have to do is to start replacing individual measurements by some unbounded value, arbitrarily large. Let's say I replace one measurement with infinity. And see how your mean will respond to you and how your median will respond to you. Again, I'd like you to pause the video at this point. Once you are ready to move on, hit play and we will discuss the solution. Now, let's consider the mean of Zi estimator. This estimator gets some measurements and will output the mean or the average value. Now, let's say I pick the first measurement, let's say 109, and I replace it with infinity. Is that going to affect the average value? It absolutely will. So my state estimator cannot even deal with one corrupt data point. One corrupt data point is going to change the entire output. So with the definition of breakdown point, it is only providing acceptable results if the number of corrupt data points m prime is 0. So the breakdown point for this estimator is 0. You have one corrupt measurement and your output is going to be biased. Now let's consider the second one, the median of the measurements. Right now, for the 5 measurements that I have, the median is going to be 105. Now let's take 109 and replace it with infinity. The median is still going to be 105. Let's take 107 and replace it with infinity. Median is still going to be 105. So far with 2 corrupt data points, my estimator is providing an unbiased output. Now take the third value, 105, and replace it with infinity. Your solution now is going to be wrong. Your output is going to be biased. So the breakdown point for this particular estimator is going to be a maximum of 2 corrupt measurements out of 5, or 40%. The final mitigation technique that we're going to discuss today is dynamic state estimation. As I mentioned earlier, under normal operating conditions, the power system can be assumed to be in what we call a quasi-steady state mode. In this mode, the value of voltages, phase angles, currents do change, but not change dramatically. The changes are slow enough that you can capture them by sequential state estimators, which is pretty much what we do in today's power systems. Run state estimator every 5 minutes, every 1 minute, every 10 minutes, depending on how slow changing your system is. Sometimes, however, this is not possible. Sometimes the dynamics are much faster than that. So from now till 1 minute from now, you're going to lose a lot of accuracy. In situations like these, you're going to have to run what we call a dynamic state estimator. Now, dynamic state estimation is a relatively complicated approach in power systems. We're not going to get into details of it here. I just would like to provide you a high-level understanding of what it does. Here, we're assuming that we have 2 sets of equations. One of them is going to be the state space equations. These indicate the state of the system and how they change based on the variations in the input. As you recall from earlier discussions, this would be x at k plus 1 equals some matrix times x of k, the state at time k, plus another matrix times input at time k, plus some error that I'm showing here as wk. The second equation that I have would be my measurements. My measurement z at time k equals a matrix h times the states at time k, plus again an error term which I call here v of k. A very common approach for dynamic state estimation is using a Kalman filter. Kalman filters operate based on a 2-step approach of predict and correct. In step 1, they estimate the state of the system at some step given the knowledge of the states at the previous time steps and the input at that point. Then in the next step, they correct this estimate by looking at the measurements that are available at that particular point in time. Dynamic state estimators are used in situations that the system changes dynamics very, very quickly. One example of this, which is quite common, is to have a microgrid. If you have a microgrid, that assumption on quasi-steady state operation is not valid anymore. Things do change quickly, and you're going to be able to capture that, and dynamic state estimation is the only way that you can do this. Here's a list of references that could be useful to you if you're interested in knowing more about state estimation. In particular, the first reference gives you a lot of different algorithms to deal with different biases of state estimation, things that we skipped in this lecture in the interest of time. In addition, there is the topic of topology processing and parameter estimation that, again, we didn't get to discuss in this course, but if you are interested, the first reference has some valuable information on that, and I would suggest that you refer to it.